Hello. So we will now provide a small introduction to the BV formalism, a brief one. So before starting with explanations, let's go over motivations as to why you should even care to begin with. Well, some motivations. First of all, the BV formalism is useful for gauge theories. Why? Why do gauge theories even have a problem to begin with? Well, one way to notice this is that when you study the kinetic operator of some gauge theory, say Maxwell, you will note that the kinetic operator, in particular, has a huge kernel associated to the gauge transformations of our field. And again, in particular, this means that if one wanted to invert this operator to find the propagator or Green's function, then such a thing should not exist, because how can you invert something that has a kernel? So you can't even define a propagator, much less start then the program of Feynman diagrams to begin perturbative computation. So already there, that's the first obstacle you encounter. Then another motivation might be that if you, by chance, end up studying supergravity, well, you will note that maybe even if you knew BRST, you would encounter a problem. Because for supergravity, what you have is that when you study the commutator of gauge transformations of these gauged supersymmetries, what you find is that normally you hope that the commutator of gauge transformations translates into the gauge transformation of a commutator of your gauge parameters. And this is necessary if you do BRST for the BRST transformations to be nilpotent, that is to square to 0. But in supergravity, this equality does not hold on the nose. Instead, it holds up to equations of motion of supergravity. So what this is telling us is that this gauge transformation is a Lie algebra homomorphism, but only on shell, only if we impose the equations of motion. And in particular, also the same holds for BRST. It's only nilpotent, the symmetry, if we're on shell. On shell, it doesn't, off shell, sorry, it doesn't hold. Another reason why you might be interested in BV is that most rigorous results involving gauge theories in the mathematical literature use BV, and also in the physics literature, when you prove renormalizability of Yang-Mills, under the hood you're using techniques from BV. So in order to understand those rigorous mathematical results, you would need to understand this technology. And finally, if you're ever using Chern-Simons, or trying to do perturbative computations in Chern-Simons, rather, then you would find it useful to use the BV technology, and we will hint as to why in a moment. But again, now, having introduced some of the motivation, then maybe we can go on to construct or imagine how one would even come up with the idea of the BV formalism, starting with the simplest QFTs possible, aka zero-dimensional QFTs, also known as integrals, okay? The way we're going to proceed is that, well, in zero-dimensional QFTs, we will have some integral of this form, like analogous to what we hope to be able to define in higher dimensions in the form of path integrals, and somehow say, for some reason, we know this action to be problematic in some sense. Maybe also there is a quadratic term. Maybe I have n fields and there's a quadratic matrix, a quadratic term that is non-invertible. Maybe there's something analogous to the one of gauge theories, or in any case, whatever problem we may encounter, the idea, the starting idea for the BV formalism will be the following. What if we add new fields and do some sort of analytic continuation? So we want to deform our integral. We will understand BV as a deformation of integrals. And what does that mean? Say, for each field, we introduce an antifield, a corresponding new direction, and we claim that our integral, our original integral, will be along the slice upon which this new field, phi dagger dagger, is equal to 0. So that will be the surface upon which our original integral was integrating, but maybe we could define some new surface. We could try to deform the contour of integration, quote unquote, in a way that we can define now a curve that is something like, well, our anti-field is equal to some function of our origin or a field. Maybe we could hope to deform that and in a way that preserves the original value of our integrals, of our observables. And yeah, it rhymes with how one ends up in the realm of complex analysis and deforming contours, even though the technique will not be on the nose that, but it will serve as a useful metaphor to think of analytic continuation. So if we were to want to deform our integral in this way, then we have some open questions. First one, how do we analytically continue the action? So let's call the original action, let's call it S0. And that one originally depended only on our fields. So we have the freedom to choose how it depends on the new anti-fields we have just introduced. Of course, this dependence should be such that when I set the anti-fields to 0, I should recover my original action. The original dependence on the original fields. So that is, well, one open question. If we are to do this extension, how do we extend our action? Second question, okay, how can we make sure that our observables are independent of the choice of f we made upstairs? So, well, yes, we're telling ourselves that we're going to somehow deform this curve, this contour of integration. Well, it better be the case that our integrals are independent of this choice, our correlators. Okay, so let's see what happens if we try to address point number 2. Let's study, let's say, just the simplest observable, the partition function, and what happens if we deform it, if we try to deform the f in question. And you see what we find, and I have assumed that I have more than one field, say. This is true for, I'm going to say that I have some list of physical fields and some corresponding one-to-one correspondence with some list of anti-fields. And for each one, I will have to impose the condition of this form, and which leads me to realize this typo. So we see, if we take a variation of the partition function, we will take a variation of this integral. That means that we will have to take a variation only with respect to the second slot of this function. So a variation of the of this f comes down. And we have to take a derivative with respect to the anti-fields. In any case, this is the final expression we get. And in order to make this independent of the variation delta f, we see that we have to make this function, aka the action, independent of the anti-fields. But that's kind of boring. That is just leading us to our original problem. We have no dependence on the anti-fields. Obviously, if that is the case, then we won't depend on this function f. But we don't want to go back to our undeformed integral. So instead, we're going to do another proposal. The new proposal will be instead to define f as a derivative of some other function psi with respect to my fields. So we will define some function psi, take its derivative, its gradient more or less, and equate the anti-field to the gradient of this psi. Now, why would this be different? Because our observables live inside an integral. And we don't need things to be 0 inside integrals. We just need them only to be 0 up to integration by parts, or we just need them to be a total derivative. And in this case, that will help us out. So now we have to make our theory, or rather, our observables independent of the function psi we use. And now in this case, what we get instead is that still we need to take this variation. But now, what we find is that what we will find is a variation of psi, but now taking a derivative with respect to our fields. So instead of f, now we have this derivative of psi that comes down. But this derivative with respect to phi, I can definitely move it via integration by parts, since I'm inside an integral. Ultimately, this leads to I erase it here, maybe at the price of a minus sign that won't matter too much, but I take a second derivative, and, well, at this point, second derivative, and now a derivative with respect to phi I. So we see, in order to make our partition function independent of psi, all we need is for this sort of Laplacian-looking operator to annihilate my measure, to annihilate my action in a way, or the exponential of my action. This Laplacian-looking thing indeed is called the BV Laplacian, and it's denoted by the symbol delta. So here we stumble upon one of the first characters that arises in the BV formalism, the BV Laplacian. And so we see, okay, we require then that for this to be invariant under any deformation of psi, then this Laplacian must annihilate my action. I write it here, the equation, and we see, well, I will put in an extra h bar parameter as is customary in our in the definition of the measure, just so that we can eventually study things in the classical limit or in some perturbative expansion in h bar. So in any case, if we impose this equation to be true, what we find is that the following must hold. You see, this is a second order operator. It has two derivatives on it. So those two derivatives either hit the first derivative hits an s, then the second derivative hits another separate s. That will give us this term. And then the other possibility is that both derivatives hit the same s, in which case we will get the second term. If we follow carefully the factors of h bar, we will find that this one is an h bar correction to this term. So we see we stumbled upon what's called the quantum master equation. We stumble upon the fact that whatever whatever our choice of s is, however we decide to quote-unquote analytically continue it, it better satisfy this equation in order for our theory to be insensitive to our choice of deformation of contour. Okay, so that seems like we're getting slowly some mileage. Then what if we study then some observable that's not the partition function, but rather maybe the correlator of some random observable O? In this case, now we would just have to add an observable O, essentially, to this integral. And it turns out the argument essentially follows identically. And we will just keep the observable O, which, by the way, can be a function both of my fields and my anti-fields. And so in any case, what we find is that the new condition for the variation of this to be 0 is that now the Laplacian, the BV Laplacian, ends up acting in both guys, and that better be 0. Assuming we already satisfy this condition, that the measure to begin with was invariant under this BV Laplacian, then what is left after we act with the BV Laplacian on the product is the following. We see, again, the two derivatives can either hit the S or the O. If one hits the S or the O, we get something like this. It can either be the derivative of the field that hits the F and the anti-field's the O, or vice versa. And, okay, so this is one term we get. The second term we get is when both derivatives just hit the O. Again, if we keep factors of h bar carefully, we track them, then we will see that this is an h bar correction, is higher order in this equation. Now, at this point, one could notice, this structure one encounters is oddly familiar to something you may know from classical mechanics courses, which is, well, it seems like we have two fields and, you know, a term like the derivative of the first with respect to one of the fields, then derivative of the second observable with respect to the other type of fields, plus the reverse, that begins to be oddly similar to a Poisson bracket from Hamiltonian mechanics. And so it seems to be the case that this term, let's call it the classical term, with this being the quantum correction, let's say this classical term seems to be saying, hey, we're in possession now, it turns out by introducing these anti-fields, we're in possession now of some sort of bracket structure that naturally appears if we try to vary our correlation functions, or we try to vary the psi that we introduced. And it seems to be the case that, well, at least up to h bar corrections, if the bracket between S, our action, and our O, our analytically continuing action, and O, if it were 0, then up to quantum corrections, it would seem to be the case that we would find that our observable, well, this equation would hold, and more importantly, our correlators will be independent of this choice of deformation. Now, one could think, well, maybe this is trying to impose some extra constraint on my S. Maybe I can use this to say, the space of S's I can use is somewhat constrained. But it turns out what really happens first is that, or rather here, one could stumble upon one of the key ideas in the BV formalism, which is to say, well, first of all, notice, the action, whenever one has a Poisson bracket like this, one can imagine this being S being some sort of Hamiltonian function, and Q being the Hamiltonian vector field for this function, acting on O. So we see that S is sort of generating a symmetry. And here we come to the key idea. What if this symmetry we associate to gauge symmetries, or also called BRST symmetries, if we make the gauge symmetries fermionic, if you've done Faddeev Popov. And why would we even do that? Because maybe it is the case that requiring that this be invariant under all my observables be invariant under arbitrary deformations, maybe that request is just too stringent, too demanding. And instead we could think, well, I don't even need it to be invariant for all observables. I just need it to be invariant for gauge invariant observables. Those are my physical observables. Those are the ones that whose correlators I care to preserve under these deformations. So we might think, if our observables are gauge invariant, then we will define this Q, this Hamiltonian vector field, such that Q of O will be 0, if and only if it's gauge invariant. But if this is 0, then this equation holds, this equality holds to 0, and therefore I don't feel the contour that I chose. Perfect. So let's try to implement this in some simple example at least to see how it would go down. Say, okay, if we're going to have gauge symmetries, or rather BRST, like some sort of fermionic fermionic version of the gauge symmetries, and suppose the reason why one would use fermionic ones is to enter in the realm of cohomology, which we will not explore much. But in any case, in order to have this BRS be a BRST symmetry, well, you could say that our fields phi transform, let's say there's just only one for a moment, and say it transforms under an infinitesimal U1 symmetry. So this is what an infinitesimal U1 symmetry would be like. Maybe that is a gauge symmetry in the problem in question. And okay, so we have to introduce a ghost that generates that gauge symmetry in this situation. And well, we introduce it such that precisely Q of phi is precisely this infinitesimal transformation. At this point, we realize, our analytic continuation for the action is now fixed. Up to some ambiguities, but you see, how so? Well, we know now what Q of phi is. We have decided to make it, well, the gauge transformations of our problem. And okay, we also know that Q of phi is, Q is some Hamiltonian vector field generated by this Poisson bracket with S. So now we see, the Poisson bracket with S is equal to this, because, well, you must take the derivative of S with respect to the anti-fields, the derivative of phi with respect to the field, plus a second term that would involve the derivative of S with respect to fields, but it would involve the derivative of phi with respect to the anti-fields, and that is 0. So in this case, only this term survives. Moreover, this is equal to 1. And so we have some sort of differential equation. Once we remove this term, we have some sort of differential equation. The derivative of S with respect to the anti-field must equal the BRST transformation of our fields. And indeed, this suggests, well, in this case of the U1, this equation holds more broadly outside only the U1 case, but sticking to the U1 example for what I write here, then this means, well, it means precisely this. I take the derivative of this guy with respect to the empty field, and I precisely get my BRST transformation. So it seems like we have begun to fix what the analytic continuation must be. Moreover, if, say, instead of U1, say we did maybe UN, and now Q maybe is the fundamental and C is a matrix, so essentially the same equation holds. Similarly here, now the antifield should be something in the anti-fundamental, such that this now is a fundamental, matrix, anti-fundamental. The same equation holds, essentially. Now, in this case, we would find that the ghosts also have BRST transformations of their own. In which case, well, for the C ghost, it would look something like this. And given just previous knowledge from BRST transformations and how they work, this guarantees that Q is nilpotent. It squares to 0, the fact that C is of this type. And well, so QFC is just CC. Perfect. That means that's what we must include this in our action. The derivative of the action with the corresponding anti-field for the ghost, and rather, I should emphasize first, the fact that our C needs to transform under BRST tells us, we must include then anti-fields also for our ghosts of the BRST transformations. And precisely a differential equation that's completely analogous to this one tells us that the anti-field is coupled in our action to the BRST transformations of the ghost. And with this, we see that now we have a perfectly good candidate for what the analytic continuation of the action should be, having simply invoked these BRC transformations in order to fix it. And let's see now what was the original condition this S had to satisfy. Focusing now on just the classical term in this action, again, one would also have to verify that the quantum corrections are satisfied, but we will have little to say for now in what follows. But focusing on this term, you see, this term in the equation can be rewritten somewhat succinctly. I will make some space here. This equation essentially can be written as 1/2 of the Poisson bracket of the action with itself. By the way, this Poisson bracket is often referred also as the BV bracket, and so I will also use that terminology moving forward. So what we have then is that the Poisson bracket of S with itself should be 0, and in order for the equation to be satisfied classically. And here, skipping ahead to one of these observations, that is going to be precisely correlated with this statement. Note, yes, if I am to take 2 BRC transformations of my field in a row, then that's equivalent first, okay, I will take the first transformation, and then I will generate the second transformation with acting again with S via my bracket. But this is a bracket, so it satisfies some sort of Jacobi identity. I invite you to check that precisely the Jacobi identity, when these two arguments are the same, leads me to the following equation, which means that if this is equal to 0, then precisely Q will square to 0. Or in a different, set rather in the opposite direction, if the BRST symmetry we started with was nilpotent to begin with, then that will turn out to guarantee that this action, at the very least, is a constant, so that the bracket of a constant with phi is equal to 0. But it turns out in this case, it's actually equal to 0 on the nose. So we see, as long as the BRC transformation we used was nilpotent to begin with, we guarantee that this classical master equation, as it's called, the fact that the bracket of S with itself is equal to 0, we guarantee that this equation then holds. Moreover, having skipped this statement, let's go back to it. the anti-fields must be fermionic. Where can that be observed? Well, for once, we want the action to be bosonic, and if our ghosts were fermionic to begin with, in order to have things like this, the fact that our transformations square to 0, then this means that for S to be bosonic, the antifields must be fermionic. And similarly here, rather, if instead since this quantity has 2 fermions, this is a boson, so the antifield for the ghost is instead bosonic. So it seems like whatever antifield, the fermionicity of the antifield is always the opposite of the one for the field. So that's what we stumbled upon. We have that we must introduce these, turns out, fermionic directions. And, well, it is what it is. If we do so and we pair it with this technology, we find a way to, construct observables that are invariant under these deformations. Finally, I also mentioned that the condition that we started from, that the phi dagger is evaluated in some sort of gradient of this form, has a very nice geometrical interpretation. You see, the fact that we have a Poisson bracket, or that we have a BV bracket, suggests there should also be some symplectic form. So indeed, we could construct then a symplectic form out of the data of the fields and the antifields. And so we find then that if we restrict, first of all, the original condition that phi is equal to 0 would translate, if I plug it in here, phi dagger equal to 0, would precisely kill this symplectic form. Similarly, if I evaluate at some condition of this form, this would also set the symplectic form to 0. So if we remember from our classical mechanics, essentially what we're doing is something like the original condition, well, or rather, our field and our antifield are sort of canonical conjugates to each other. And it's like X and P from classical mechanics. And setting, in order, the original equation or the original integration contour was setting, say, P to 0, was setting one of the two to 0. The statement now is that whatever curve we choose to set to 0, it better be something that is like a conjugate canonical variable. So if this is my original field, the other direction, or rather, in symplectic geometry, if I had the x, p is a canonical conjugate, but it's not the only one. I can precisely deform p plus some function of this form, and that would be another good canonical conjugate. Just to say, the thing we set to 0, the function, essentially we're setting phi dagger minus this to 0. That function must be a canonical conjugate in and of itself. Said in more mathematical terms, whatever contour we choose, it must be a Lagrangian contour. Like the symplectic form must pull back to 0 when pulled back onto the surface in question. So we see that it has this data has some form of geometric interpretation. So again, in summary, well, what do we do in order to do BV? First, we must add C-ghosts so that we have a BRST transformation associated to the gauge symmetries of the problem. Then add antifields for both the fields and the ghosts for the BRST transformations. Sometimes these antifields will be labeled by some sort of Lie algebra index in the same way that the ghosts for the BRST are. And having introduced all of this new content, well, we analytically continue our action so that our original action S0 goes to S0 plus, well, the antifields paired up with the BRST transformation of the field, and the antifield for the ghost paired up with the BRST transformations for the ghost. If this holds, then we find that the correlators, as a function of the psi we choose, the contour we choose, are independent of psi if these observables are gauge invariant, and if our action satisfies the classical master equation, which holds if the BRST transformation squared to 0 to begin with. And, well, it's worth emphasizing that we stumbled upon a set of, fermionic symplectic geometry. Fermionic symplectic geometry appears naturally from these sets of constructions. Okay, now let's just give a couple examples. Example number 1, Maxwell. You see, well, I will assume Maxwell has the action in the following form. I will use form notation for what follows. Here we have the BRST transformations of our Maxwell field. A transforms, well, by the typical gauge transformation. C, in this case, is simply 0. Having knowledge of the BRST transformations, we can immediately then express the action, the new action, the analytically continued one, quote unquote. So we have a field A dagger dagger paired up with the gauge transformations of A. In this case, normally, if I were to write the components of this field, I would write something like a partial and a mu index in this place, in which case I would write something like an upper mu index on the anti-field to pair up into a covariant or invariant thing. In this case, instead, I will interpret it in a different sense. I will use the Levi-Civita symbol, let's say in 4D, that has to lower the upper index and instead give me 3 antisymmetric indices. In any case, the main point is that I will think of A dagger dagger as a 3 form, is a whatever form degree I need so that it pairs up with my ghost that is a 1 form. 3 plus 1 gives me 4 in 4 dimensions. That gives me a top form that I can integrate, say, over my space-time 1,3. Similar thing here. I will add now the anti-field for the ghost paired up with the BRST transformation of the ghost, but since this one is 0 in this case, this term doesn't even appear. Now, taking a look instead at the symplectic form, which for fields can be written like this. So we see, well, we will have some variation of the anti-field wedged with the variation of the field plus the similar thing for the ghosts. And again, this is sort of the infinite dimensional analog of an equation like this. A form is like a small variation of x wedged with a small variation in p. In this case, a field with the anti-field. Yes, this would be the infinite dimensional generalization. And then the question is, the statement would be if instead of the original integral would simply, or path integral in this case, would integrate when this is set to 0 and this is set to 0, how can we deform that condition while preserving the statement that this symplectic form still vanishes in the new surface upon which we integrate? In this case, this Lagrangian, ergo the letter L, even though the word Lagrangian here is used completely independently from the Lagrangian of the theory. It's just that, in symplectic geometry, Lagrangians are subspaces that kill the symplectic form when pulled back. When the pulled back of the symplectic form gets killed upon them, plus some condition about maximal size. But in any case, so the condition that we find here instead now is, okay, I will use Lorentz gauge hidden in a notation that maybe it's not familiar to everybody, but it's worth commenting. So I'm going to impose that the d dagger of A is equal to 0. So A gets killed by the d dagger operator. Notice the dagger has nothing to do with anti-fields in this context. The dagger is simply the star of d star, where star is the Hodge dual. Maybe up to a minus sign, that depends on dimensions. If I impose this condition, if we write things in components, we would find that this is precisely the same as saying that the divergence of A must be equal to 0, aka Lorentz gauge. So we will impose this on my fields. Moreover, we will impose that my anti-field is instead equal to the d dagger of someone else. There exists some field B such that taking its d dagger will give me my anti-field. Okay, extra condition. Finally, I will impose that the anti-field for the ghost dies out. Like, that's the original surface we started with, and we will just retain that one. But for the other ones, we will do this transformation instead. Notice that, and let me write this better. Notice that if we plug now these conditions back into the action, what we would find is the following. For once, the anti-fields, as we mentioned, will be now instead the D dagger of some field B wedged with the D of C. Afterwards, well, this term wasn't even appearing in our action to begin with, but we can impose the condition that D dagger is equal to 0 by some sort of Lagrange multiplier. So I will write it in this form. So I will include it so that it imposes the condition of invariance in this way. And so we see, if we plug in these conditions back into the action, what we find is precisely the Fadeev-Popov action one would get after gauge fixing in the way one knows from usual QFT textbooks. We will see, after integration by parts, this term precisely looks like B box C. D dagger composed with D in this way is related to the box operator. And here we would find instead the usual Nakanishi-Lau group paired up with the gauge fixing functional, in this case the Lorentz gauge. So we see that the fact that it's reassuring, the fact that we land on the same action, it gives good evidence that this is a good choice to gauge fix the theory. And moreover, we can check that it kills the symplectic form easily. So again, if I plug this into this slot, well, we would have D dagger B, but D dagger satisfies an integration by parts equation, so I can move its D dagger to act on A. But now D dagger on A is equal to 0. So indeed we see that once we plug in these conditions, we find that our symplectic form vanishes, our fermionic symplectic form. Okay, so that covers a bit of the Maxwell example that I wanted to mention. Finally, since I mentioned it in the introduction, let's say a few things about Chern-Simons. Again, we will run through the same machinery. Say we have some group SUN. The gauge transformation for A will look something like this, where the A is the covariant derivative using the connection A. C is going to be some adjoint valued field, some n by n matrix, since the group is SUN. Similarly, now the gauge transformation, or rather BRST transformation for the ghost, is the same as for the finite dimensional example, but now C is, of course, the field over space-time. And now these two BRST transformations, now going over again the same logic, will land us in this action. Again, we will have the anti-field paired up with the BRST of the gauge field, the anti-field paired up with the gauge transformation of the ghosts. Okay. Now, if we choose our forms to be fermionic, and here comes the main simplification of the problem. You see, we can pair up all of our fields, the C's, the A's, the A daggers, C dagger daggers. We can pair them in a superfield that I'm going to denote by the mathcal A. So notice that here we have a 0 form, we have a 1 form. Notice that Chern-Simons lives in 3 dimensions, say R3. Then if this is a 1 form, then this needs to be a 2 form. Similarly, if this is a 0 form, then this needs to be a 3 form. So again, 1 and 2. Just to say, for every form degree, we have a field. So if we pair them up together, then this lives on a form of arbitrary degree, or the direct sum of all degrees, which we denote by this dot. Okay, and moreover, if we make forms have fermionic degree, like forms, I mean things like the symbol dx mu and the Ram differential itself, they will both be fermionic, meaning that, for instance, the ghost C will anti-commute with each of them. Then in this case, now A has a consistent fermionicity. And that's the reason why we make this somewhat potentially artificial choice. You see, C is a fermion. A normally is a boson, but it comes paired up with a form, a degree 1 form, so it's going to be a fermion. Same thing here. Antifield, this one should usually be a fermion, and it's a 2 form, so the 2 form degrees are bosonic. So again, this thing is a fermion, and well, I leave you to check that this one is a fermion as well. The point is, we can build a superfield, quote unquote, arbitrary form valued superfield that encompasses all of our fields and our antifields. And it turns out, and it's a cute exercise to check this, that the action S we found here can be precisely obtained by the same Chern-Simon's action, not evaluated on the single physical field alone, but rather evaluated on the superfield. So that is one of the major simplifications of the theory, that you can use the same action and evaluate it in a form-valued field, and Feynman diagrams, the combinatorics, simplifies substantially, given that you only have to keep track of one superfield. Yes, and notice, by the way, the fact that I use a plus sign in here is exactly associated to the fact that I already assumed that fermion things don't anti-commute with form degree. Otherwise, there should be either a minus sign here or here. So it was implicit in the construction to begin with. In any case, we see that for Chern-Simon, the simplification arises because we write, or we are able to write things in terms of these superfields. I think one could say some extra things about the symplectic form, but we'll leave that for other opportunities. And I hope this was a somewhat insightful and light enough introduction to the BV formalism. Thank you very much.